Okay, so welcome to this next video in the playlist on functional analysis. So we're continuing with our study of metric spaces, and specifically with the property of separability of metric spaces. So recall that separability refers to a property of metric spaces, and the definition is that a metric space, let's say xd, so let me write something down. So if you have a set x with a metric d defined on it, which is a mapping from the Cartesian product of x with itself onto the non-negative real numbers. If you have a metric space, it's said to be separable. Oh dear, no, I've spelt it wrong again. I've been doing this throughout many of the videos. Separable has an A there. I discovered when I actually uploaded them onto YouTube and it corrected it for me. Separable. So I've learned something from doing this. Separable, it's a metric space is said to be separable if what? If there exists, I'm getting distracted by my spelling, how awful my spelling is. If there exists a set S, which is a subset of the set of the whole set X on which the metric is defined, such that S is countable, so that's the first condition, and secondly, S is dense in X, meaning that every point in X is our limit point for the set S. So if I draw a picture, here's our metric space X, and it has some metric defined on it D, and you have some set S in here. And basically, if you take any point, little x, out here, and you draw a ball of size epsilon around it, in this case, the set S is not, the way I've drawn it is not, it is not dense in X. So if I take any point, little x, and I draw an open ball, so that should have dashed lines rather than a solid line, open ball around X of size epsilon, then there should exist a point of S within that ball, whatever size epsilon you take, whatever point X you take within the metric space. Okay, so that's just a reminder of the definition of separability. Now we're going to discuss separability of the discrete metric space. Separability of a discrete metric space. That's what the topic for this video. Discrete metric space. Okay, so separability of a discrete metric space. So just recall what a discrete metric space is. You take a set X, which could be finite, it could be countably infinite, it could be uncountably infinite. It's just any arbitrary set, and you define the metric as follows. You say that the distance between X and Y, where X and Y are 2 points of big X, is either equal to 0 if X is equal to Y. So if they're the same point, if you're asking what's the distance between X and itself, then the distance is given the number 0, and it's equal to 1 if X is not equal to Y. So there are some nice images of what this means if your set is a set of 2 points. So if X is a set A and B, then you can just view it as basically 2 points, let's say A and B, which are a distance 1 from each other, and obviously they're distance 0 from themselves. So that's the way of viewing a discrete metric on this set here. If you've got a set of 3 elements, X is equal to A, B, C, then you want 3 points which are all the distance 1 from each other and a distance 0 from themselves. So that's just an equilateral triangle like this. So A, B, C, where all of these sides are of length 1. That's a nice way of visualizing the discrete metric on a set of 3 elements. And if you've got a set of 4 elements, then it's the generalization of an equilateral triangle. It's a tetrahedron. So can I draw a tetrahedron? I'll have to do it sort of kind of like this, maybe. Yes, I can draw a tetrahedron. Okay, so this is A, this is B, this is C, and this is D. Well, it doesn't matter which ones you give the letters, obviously, to. All the side lengths are equal to 1. So there are, how many sides there? There are 6. So they're all of length 1. Okay, we'll cut this video short and continue on the next video. Someone is beckoning me.